Welcome, everybody. Today's lesson is about intermolecular forces. But before we go to the intermolecular forces, we have to understand the scope or the domain of intermolecular forces. So I just want to recall the type of bondings between atoms and then jump to the intermolecular forces. So let's start to recall the types of bonding in chemistry. As we remember, we have the type of ionic compound, and this type of bonding mixed the non-metal with metal. And just like a good example about that, which is an ACl, this is a table saw. It appears as 3D lattice structures, repeated patterns of positive and negative ions. And the structure of ionic compounds is giant because it's a repeated pattern. Okay, so we're done with ionic bond. And we have another type of bonding, which is metallic, and actually it presents in metals like, for example, iron, copper, gold, silver, etc. And the structure of metallic bonding is giant. Okay, let's go to the covalent compound. The form of diamond, like it's a repeated pattern, tetrahedral of carbon atoms that are bonded tetrahedrally to each other. And they're in a lattice, and they're in 3 dimensions, and it has a lot of bonds, a strong and rigid structure. But if we go to the simple one here, the simple molecules, I just want to give you an example of simple molecule like water molecule. This water molecule, and we have another water molecule. It says that we could have a possible interactions between these simple molecules, and this is the scope of intermolecular forces. So the intermolecular forces present in a simple covalent compounds and appears between molecules, not within a molecule. So technically, we're going to study this type of interactions between molecules. All right. We call the type of intermolecular forces between molecules van der Waal forces. And the van der Waal forces represents the type of interactions between molecules in chemistry. So what are the type of van der Waal forces, and how can I represent them in a proper way? We'll start with the first part, which is the simplest one, and it's called instantaneous dipole, induced dipole, or London forces. And by the way, in some books you could find a temporary dipole. It has another name, temporary, or dispersion forces as well. And what you have to put in your mind, this type of interaction presents in all simple molecules. Okay, these are in simple molecules and overall. And you have to put in your mind something. We don't call this type of interactions in here as a bonding. It's not a bond. It's just like interactions or attraction forces between molecules. So let's go again here. The instantaneous dipole, induced dipole, here, present in all simple molecules in the universe. Okay. Let's go to the next type of van der Waal forces, which is permanent dipole. Technically, this type of intermolecular attraction present in polar molecules only. And we have another, or let's say a special case of the permanent dipole, and this type is called hydrogen bonding. So you have to put in your mind the hydrogen bond is a case of the permanent dipole. And we will discuss it later. So we're going to start with the first one, which is instantaneous dipole, induced dipole. How does this type of interactions occur? I want to give you a good example. Suppose that you have a small molecule. We have another molecule in here. We have another molecule, and we have another molecule. And it says that we have interactions between these molecules. What is that? In all molecules in chemistry, we have a lot of electrons, right? So these electrons move through the molecule at certain type, or let's say at certain time. You could have an area that contains a lot of electrons in this area of the molecule, and that's why it becomes partially negative, whereas in this molecule, the movement of electrons gives this part to be partially negative, and thus it becomes partially positive. So as a result of that, you will notice that there's establishing of attraction forces between the molecules. Since you have partially negative and this is partially positive, these are oppositely charged particles, or let's say molecules, and that's why we have interactions between them. And that's why we call these interactions instantaneous dipole, induced dipole. Why we call it instantaneous? Because it's temporary, it doesn't last for a long time. This number of electrons in here, as we can see, they can move to this part in here, or let's say come in here, like they start to move across the molecule. So once their movement give a partially negative and partially positive, you will have interactions, or let's say attraction forces between the molecules. Okay, and you have to put in your mind, is it possible to have repulsion forces between molecules? Yeah, you could have a molecule in here that has a negative charge and you have a negative one here, and you could have a repulsion force. But the question now, what are the factors that this type of interactions or intermolecular forces depend on? First of all, it depends on the number of electrons. Okay, you can deduce it from the figures in here. As the number of electrons increases, the attraction will increase. So if you have a compound that contains a lot of electrons, it will be higher in attraction, and it will have a high melting or boiling point. In addition to that, it depends on the number of contact points. Let's take that in terms of a clearer way. Okay, look at these molecules. First of all, if you look at CH4 molecule, if you want to count the number of electrons, carbon has 6 electrons, and for hydrogens, we have 10 electrons in this case. Here you have 6 hydrogens, means 6 electrons, plus 12, and you have 18 electrons, etc. It will be higher in electrons. So as we can see, we are expecting the interactions in this molecule to be greater than in this molecule. In this one, here contains more electrons, and we're expecting to have an instantaneous dipole-induced dipole interactions due to the greater number of electrons in here, and then here, and then here. The second factor that the instantaneous dipole depends on is the number of contact points. The number of contact points depends on the length of the molecule. So let's just go in here. The number of contact points depends on the length of the molecule. Okay, so as we can see, the interactions between the molecules in here, just like only one here, but in here you could have this one, and here you could have interactions. And the length, as the length of the molecule increases, you will have greater contact points in this case, and this indicates to stronger intermolecular forces, and these interactions will be reflected on their melting point. So my question here, which of these compounds, or let's say which of these molecules you expect to have the greatest melting point, or let's say the highest melting point or boiling point? We're expecting here because it contains a greater number of electrons and it's the longest molecule among these in here, and that's why you'll have more contact points. So as the number of contact points increases and the number of electrons increases, the strength of the instantaneous dipole will increase, and that's why it will have higher melting point and boiling point. I just want to explain this in terms of these two compounds. You have C5H12, which is a pentane, and as we can see, we have pentane that is in a straight chain, as we can see here. We could have another molecule of pentane, and we just find that we could have a lot of interactions between the atoms in this molecule, a lot of contact points, because it's longer molecule, but again here it's branched. And since it's branched, you notice that if you have the two molecules, they will start to close, to approach from each other. And technically, you notice that per each two molecules, you probably have almost 2 contact points, and that's why you have less attraction in this case, and we're expecting to have lower melting point than this, which could have higher melting point.